Hello, my name is Benjamin Selinsky. I'm a Master's of Science student at University of Houston Clear Lake, and my talk is entitled The Particulate Exposure Assessment of Metal Casting Operations in a University Foundry. So let's start with an introduction. What is the foundry? Universities teach metal casting and foundry operations as part of a standard mechanical and construction engineering curriculum. From small-scale casting operations, students gain practical experience in handling molten metals, producing custom objects, and further their metallurgical studies. Numerous studies on the health and physical hazards of industrial foundry operations and their workers have been undertaken since the early 1900s. But since small foundry operations are on a drastically reduced scale from industrial applications, they receive very little attention. And also, since university foundries are under the auspices of general laboratory safety programs, routine exposure assessments of small foundry operations are rarely performed. So, foundry processes are divided into ferrous and non-ferrous metal castings. Ferrous and steel foundries are large-scale productions that produce products that weigh thousands of tons using very high temperatures. While large-scale ferrous operations of iron and steel manufacturing make up over 80% of the total American foundry output by weight, non-ferrous foundries such as aluminum, brass, and bronze are much more common and produce small parts and fittings with much smaller outputs. In industrial settings, different parts of the foundry process are performed in separate areas with specific health and safety precautions and must follow strict regulations on worker health and safety. NIOSH has had guidelines in place for foundry operations since the 1970s, and all foundry workers are covered under OSHA rules. But at universities, instead of ferrous foundries, we generally use the lower melting point of aluminum, about 666 degrees Celsius, and the low cost of scrap material as a major factor in choosing aluminum for teaching casting. The lower melting point allows for small electrical or gas furnaces and standard steel tools to be used rather than specialized temperature-resistant materials and coke-fed furnaces. Many hobbyists and artists also use the small-scale, even homemade foundries due to their simplicity and low cost. In the small scale and limited physical space of university teaching laboratories, these operations are commonly contained within a confined area, such as a purpose-built laboratory. The coalescing of practices into a common area increases the possible exposure to toxicants and hazards associated with these processes unless engineering controls are included into the design. Now, universities commonly teach what's called the lost mold method of casting. The typical teaching foundry processes include the four following steps: the preparation of the molds, the melting and casting of metals into molds, the cooling and removal of the molds, and the finishing of raw castings. The lost mold method involves the creation of a mold with a top and bottom form that contains the cavity in which the molten metal is poured. The form is created by pressing dense sand around an initial object, then removing the object, creating a negative space for the molten metal. The sand must be able to be compacted and allowed to bind, therefore maintaining its structure when separated from the original mold. Green sand is also commonly used, and it is a mixture of sand, clay, and carbonaceous earth, which normally has a chemical binder, including some generic organic solvents, and it's very common. In industrial settings, the melting of metals is performed in large batch couple of furnaces that use coke and air to heat the metal to its melting point. The furnaces require the control of input gases and oxygen intrusions and are very expensive to operate. Small-scale foundries found in teaching programs melt aluminum metal in what's called a crucible furnace. Now, this type of furnace contains a refractory crucible inside of a ceramic shell, heated with either electricity or fired with natural gas. The equipment is relatively small and easily controlled with minimal oversight, yet the high temperatures reached during melting also produce a litany of particulate emissions, including metal particulates and fumes. And the pictures you have here shows the industrial cupola, and also the one on the small scale is actually a homemade version for a hobbyist. Now, pouring the molten metal into the sand mold is a manual process in small-scale foundries. The crucible is raised from the furnace using temperature-resistant tongs, normally requiring two people to properly lift and pour the metal to minimize spillage. Once the molten metal hits the sand casting, any chemical compounds included in the sand for bindings are volatilized due to the high temperatures. This process also involves inorganic fumes from minerals trapped in the sand particulates. After the casting is cooled, the sand mold is broken off of the casting and discarded. The finishing process begins by the removal of the gadding by mechanical saws or grinding. The casting is then cleaned using grit or tumbling devices to smooth out any burrs or imperfections in the casting. To create a smooth finish and remove any chemical oxides that may have formed during casting, sandblasting and grinding are commonly used. These physical processes fracture and break down the metal and sand particulates into smaller sizes that are then spread throughout the foundry atmosphere. So let's discuss the history of particulate hazards in the foundries. Respiratory disorders were common among early foundry and metal workers. Industrial hygiene studies from the 1920s found pulmonary fibrosis in nearly a quarter of steel casting workers. Workers involved in the sandblasting and finishing of metal castings were found to only have a 1 to 2 year window of good health before they would be normally stricken with debilitating lung diseases. Foundry workers were also discovered to have a mortality rate from lung cancer that was 133% higher than the expected rate. During the 1950s, many studies were conducted in the U.S. that positively correlated respiratory diseases, including bronchitis and lung cancer, with a chronic exposure to one particulate, airborne silica. Silica, also called silicon dioxide, also called quartz, is one of the most common ingredients on Earth. It's found in rock, sand, and soil, everywhere. The chemical properties of silicon dioxide molecule allow it to form intermolecular bonds with itself to form crystalline silica superstructures. These superstructures can form either in amorphous clusters, such as glass, or in repeating patterns of crystalline silica. Naturally occurring silica crystals are too large to be considered a health risk since their particle size is normally too large to reach the alveoli of the lungs. Instead, these particles are trapped either in the mucosal lining of the nose or throat. The foundry processes, though, physically alters the structure of silica crystals. Crystalline silica structures are formed when the sand used in creating molds is exposed to rapid heat during casting. Also, the grinding, sandblasting, tumbling, and shaking of the molds physically breaks down the sand particles into much finer subdivisions called respirable quartz. Respirable quartz includes the common crystalline forms of silica that makes up quartz, cristobalite, and tridymite. These fragments are kept aloft in the atmosphere longer due to the decrease in their settling rate, which increases the chance of them being inhaled. These fragments are small enough that they can penetrate through the turbulent airflow and branches of the nose, throat, and lungs and reach the gas exchange membrane of the alveolar spaces. Upon reaching the alveoli, the body's defense mechanism of pulmonary macrophages attacks any foreign particles and releases enzymes to break them down. Unfortunately, the macrophage enzymes cannot destroy silica, and instead damage the alveolar surfaces, creating scar tissue. The scar tissue disrupts the gas interchange and results in both decreased oxygen flow into the blood and a decrease in carbon dioxide exchange from the blood. This is the cause of the occupational lung disease called silicosis. Symptoms include shortness of breath, cough, bluish skin, chest pains, infection, and fatigue. Long-term studies have linked silicosis to an increase of respiratory failure and lung cancer. Lung cancer mortality data in foundry workers, especially those exposed to abrasive silica particulates, showed an increase of death three times higher than workers without the exposure. Small-scale, specific construction tasks were also monitored, including concrete cutting, the use of hammer drills, and masonry. Results from these studies by sampling airborne particulates resulted in recommendations of various engineering controls and personal protective equipment to reduce silica exposure. Besides silica exposure, metal fumes are a serious threat to pulmonary health. During the melting of metals, some of the metal can vaporize and later condense into fine airborne particulates called fumes. These fume particles are very small, normally less than 100 micrometers, and sail off for very long periods of time. When metal fumes are inhaled, they can reach the alveolar spaces. Metal fumes have the same effect on the macrophages as silica and can create the same scarring tissue. If exchanged in the lungs, these metals can be a source of toxicants that are linked with pulmonary and cardiovascular damage, neurological and kidney disorders, and cancerous neoplasms. Aluminum fumes have been directly associated with tingling in the extremities, nausea, asthma-like symptoms, neurotoxic disorders, and early onset Alzheimer's. Occupational exposure of metal fumes has been studied to determine exposure levels in welding operations. Those studies resulted in the recommendation of standard engineering controls, including elephant trunks, venting fumes away from welding operations. Other small-scale operations included jewelry repair and dental filling engineering. Any health hazard that may arise from airborne particulates must be correlated with exposure rates. In an industrial foundry worker, the long-term chronic exposure data is collected and compared with health and safety standards. Since all aspects of foundry operations occur in a confined space, to determine if our students or staff in a university foundry are at risk of acute or chronic exposure of silica and metal fumes, an exposure assessment must be performed. The legal limit of exposure is determined by OSHA's permissible exposure limit, for respirable silica and aluminum dust. This limit does not represent the desired exposure level below which harm cannot occur. Instead, NIOSH's 8-hour recommended exposure limit and ACGIH's threshold limit value are used as benchmarks for safe practices. And here we can see OSHA's PEL is 10 milligrams per cubic meter divided by the percent quartz plus 2 over 8 hours. NIOSH's REL is 0.05 and ACGIH's TLV is 0.10 milligram per cubic meter for respirable silica. For aluminum, you'll see it actually looks at the total dust and the respirable fraction of 15 and 10 milligrams per cubic meter. The purpose of the project is to assess the human exposure to respirable silica and aluminum fumes during routine university foundry operations. The significance of this project is to minimize the acute exposure to hazardous particulates created during small-scale foundry operations. Startup foundries, schools, home casting projects, and hobbyists will benefit from knowing what kind of hazard exposures can occur during the casting process. The assessment will be performed by collecting personal air samples during foundry operations and measuring particulate concentrations by an analytical laboratory. The sampling data for the project will be collected at Texas A&M University at Qatar's Hot Works Laboratory Room 22. Sampling apparatuses will be attached to the outside collar of the personal protective equipment of the subjects performing the foundry operations to sample the subject's breathing zone. Subjects will wear the samplers during all aspects of the foundry operation, including the preparation of molds, melting and casting, cooling and removal of the molds, and finishing of the raw castings. Upon completion of the foundry task, or the required air volume is reached, the samples will be removed and sealed into a certified shipping container with chain of custody and sent for analysis at an approved industrial hygiene laboratory. Samples will be collected during the foundry operations by at least 2 separate personnel, each wearing a personal sampling apparatus. The foundry operations should be repeated multiple times using different personnel at a variety of times to account for variations in foundry operations. Personnel wearing the monitors will not be stationary and will move within the confines of the foundry operations room to complete each task in the foundry process. 2 to 4 stationary sampling apparatuses will be placed inside the room in the areas where there are the theoretical highest exposure rates to silica and metal fumes, i.e. adjacent to the crucible and metal pouring and next to the metal finishing station. For the sampling apparatus, a pre-weighed PVC or mixed cellulose filter will be placed into a sample holder with a cyclone attachment. The cyclone is required to remove any silica that is larger than the respirable limit of 10 microns. The filter assembly will be attached to a pre-calibrated personal air pump to sample the air at the recommended rate of around 2 liters per minute. The method requires a sample volume between 400 to 1,000 liters of air, depending on the method. Each method requires the filter to be weighed out prior to and post, and then the filters, once they're in the laboratory, will either be acid washed to remove organic material and digested, or reduced to ash in a furnace, depending on the analysis. Here you have a photo of a gentleman who is actually wearing a cyclone. The air is brought into the cyclone, larger particles are removed, and there's a pre-calibrated sampling pump that just attaches to the belt. The sampling of the air for respirable silica will be performed by following one of 2 approved methods, NIOSH 7603 or NIOSH 7500. NIOSH 7603 was developed to determine the total respirable quartz and coal mine dust using infrared absorption spectrophotometry, or what we call IR. In IR, the sample is bombarded with radiation in the infrared spectrum. The sample will absorb select wavelengths depending on its molecular structure, and that can be compared to the known spectrum of quartz. NIOSH 7500 method was developed to determine the percentage of major silica polymorphs. That's the individual structures, the different structures that actually can occur of crystalline silica. In this case, quartz, crystobalite, and tridymite. Although there are about 5 more of these structures, they're much more uncommon. This method uses X-ray powder diffraction, or what we call XRD. During XRD analysis, X-rays are passed through a sample and are deflected, or really diffracted, as it passes through the crystal. From this information, the crystal structure and composition can be determined. The sampling directions for both methods are nearly identical, with differences only in the method's assay and cost per sample. NIOSH 7603 can only report respirable quartz concentrations, while NIOSH 7500 can only differentiate between the multiple crystalline structures of silica. Now, the sampling for air for aluminum fumes will be performed using NIOSH 7300. This method was developed to determine the concentration of metallic elements in air filter samples by inductively coupled argon plasma atomic emission spectroscopy, or ICP-AES, or ICP for short. An ICP AES uses inductively coupled plasma to excite the atoms of a sample, which then radiate electromagnetic radiation specific to each element's molecular characteristics. This method will provide simultaneous elemental analysis for a wide range of trace elements, one of which is including aluminum. The sampling requirements for NIOSH 7300 is very similar to the sampling requirements for the silica, with only some minor alterations in sampling error rate and filter composition. For the analysis, the filter will actually be digested using acid, dried, and then diluted using an appropriate solution for analysis. Since the sampling equipment and analysis must be rented and performed by a qualified analytical laboratory, the sampling analysis of airborne particulates is quite high. Total sampling cost of this project is estimated to be up to $1,920. This cost may be reduced through laboratory programs where sampling pumps and equipment rentals are provided at no cost depending on the analytical agreement, of which we will try and do. If the costs are reduced significantly, more samples will be collected. Expected results for this project will be included in a data table comparing the 8-hour time-weighted averages of the sampled foundry air to the OSHA PEL, NIOSH REL, and ACGIH limits for respirable quartz and aluminum particulates. It is expected that the sampled concentrations may approach the NIOSH and ACGIH exposure limits, but will probably not approach the OSHA PELs. The exposure limits are based upon risk assessments for chronic exposure, and as we defined risk as defined as a probability of occurrence, by lowering the amount or number of occurrences, therefore the risk is lowered. Students using the foundry will not be constantly exposed to foundry air, therefore the exposure risk for them should be minimal. The major risk is for staff or researchers who will use the foundry more often. Based upon these comparisons, engineering or administrative controls will be recommended to identify, control, and eliminate health hazards. Examples of such controls include the addition of ventilation trunks, increased room ventilation through air conditioning systems, or the wearing of personal dust masks or respirators. Thank you for your time. I hope you enjoyed the talk. Here are the references. And feel free if you have any questions. Thank you. Have a good day.